Hello and welcome to this new video. In this video, I'm going to cover section 1.4 about limiting probabilities of some Markov chains. We already observed that in some cases, the transition probability matrix of a Markov chain converges or seems to converge to a matrix, a limit matrix with identical rows with positive entries. Okay? And I asked you to do a Python exercise to check that in some case. Now, we are going to give necessary and sufficient conditions for this to be true. And we will give a name for the situation. So we'll say that if this situation happens, we'll say that the Markov chain or the transition matrix of it is ergodic. So what does ergodicity mean? Means here in this case. So it means two things. So Pij to the n, which is the ij entry of the p to the n, exists and is independent of I. So it's the same for all rows, and the limit is positive strictly. Okay. So this is just a translation of the fact. If you think of terms of matrices, it's easier actually. So when you iterate p to the n, we will see conversions toward a limit matrix with positive entries and identical rows. Okay, and in this case, the identical rows are probability vectors because they sum to 1. Okay, so the limit matrix is also a stochastic matrix. And of course, we shall see examples. So the limit vector P0 PL is called the limit distribution of Xn. Okay, so this happens. It's not true for all Markov chains. It's true for what we call ergodic Markov chains by definition. Yeah, so this is what I was saying orally. So it's useful to denote the limit matrix by capital Pi. Okay. Now, remark, let us see what does this mean in terms of distribution. If Xn is ergodic, then the conditional n-step transition probability, Pij to the n, converges to some positive number Pij. So what does this mean? It means that so it's independent of I. So this conditional probability is actually independent on this condition on I. So we say that Xn is asymptotically independent of X0. So when n is large, the chain, if it's ergodic, forgets about its starting point. Okay? So this is the meaning of ergodicity here. So we have a kind of asymptotic independence for n large. Okay. So, and also note the following. If we write the unconditional probability, P of X, so the probability that we are at state j at time n, if you write the conditional probability, the total probability formula, you get that. Right, so you condition on x0 equal I. And when you let n tend to infinity, also when you let n tend to infinity, this is a finite sum. So the pi ij to the n converges to pi j, and this is doesn't depend on n. So I can put the pi j outside the sum, and I am left with sigma of px0 equal I, which is 1. Okay. So otherwise stated, pi j represents the asymptotic distribution of Xn. Okay, so when n is large, it's easy to compute in the case of ergodic chains. It's easy to compute or to approximate at least the probability that Xn is in state j. So what is the meaning of pi j? It tells me the proportion of times the system spends in state j. So actually, since pi j is a probability vector, so state 0 will be asymptotically visited pi 0 time, a proportion of pi 0, and state 1 will be visited, or the frequency of visiting state 1 will be pi 1, and so on. Okay, and all these numbers are positive. Okay, So we say that xn converges in distribution to a random variable with distribution pi. Okay. So it's a kind of constant distribution at when n is large. A corollary of this definition is that if you have an ergodic Markov chain with limit distribution pi, then small pi is the unique probabilistic solution of the equation pi equal pi p. And note that the order is important because when linear algebra we distinguish between row vectors and column vectors. So this is row vector equals row vector times a matrix, and we shall see examples in the exercises actually. So if you like, we say that pi is the left eigenvector of p. So it's the right eigenvector of the transpose. Okay. So if I write this into components, this is equivalent to a linear system. It's very important actually. So when I ask you to find the limit distribution of an ergodic chain, you have to solve a linear system, okay, usually of small size, 5, 6 maximum, because otherwise you will need a computer. So, but if you solve this, actually, you will find infinitely many solutions because it's an eigenvector, it's an eigenvalue problem. But if you add the condition that the sum of the entries of pi is 1, then you'll get exactly one solution. And you shall see this in the exercises. So finding the limit distribution of an ergodic chain is equivalent to solving a linear system. Now, why is that? Because by assumption, by assumption, p to the n converges to the limit matrix capital pi with identical rows and positive entries. Therefore, when I multiply to the left by alpha, by any alpha, any probability vector alpha, alpha p to the n converges to alpha capital pi. And you may check that for any alpha, alpha capital pi is small pi. Check that if you like. Because for a reason that alpha is a probability vector. So check that when you multiply the limit distribution to the left by alpha, you get a constant vector. So it's independent on alpha. And so in particular, if you take alpha equal pi, we'll get two things. So pi times p to the n plus 1 converges to pi. And if I write pi to the n plus 1 as pi n times pi, so then this converges to pi. So the product converges to pi p. And so by uniqueness of limits, we get the equation pi equal pi p. Now, why is it unique? The system, the linear system is unique. The solution of the linear system is unique. Okay, because we do the same thing. If pi prime equal pi prime p, if you apply p at each time, so you get pi prime p equal pi prime p squared, and so on. So you'll get, when each time you multiply by capital P, you change nothing. So pi prime p to the n is equal to pi prime, and you can prove that by induction if you like. So it's constant actually. So pi prime, so from the one hand, pi prime p to the n converges to pi because of this. So replace alpha by pi prime. Okay, but this is constant. So we have two limits, pi prime and pi, and by uniqueness of limits, we get pi prime equal pi. Okay, not difficult. And this limit distribution has several names. You can say it's a stationary distribution, it's an invariant distribution, it's an equilibrium distribution, or you may say it's a steady state distribution. Okay. Why do we call it stationary? Because if we start with this distribution and do the iteration, all the iterates will have the same distribution. Okay. So if we start with x0, if x0 has distribution p, then when you multiply by p to the n, as we observed before, you change nothing. So we are still at pi. But pi to the times p to the n is the distribution of xn. So xn still has the same distribution pi. So if you start with this equilibrium distribution, so x0 has distribution pi, then x1 has distribution pi, x2 has distribution pi, and so on. So it's an equilibrium or stationary distribution. And we already observed that this stationary distribution is what we call a left eigenvector, because it satisfies the equation pi capital P equal pi. So when you do the transpose, you'll get capital P to the T, the transpose of capital P times the transpose of small pi is the transpose of small pi. Okay, so according to the discussion above, an ergodic Markov chain has a unique steady state or stationary distribution. But the converse is not true. And I'll give you an example. If you consider this simple Markov chain on two states, 0, 1, 1, 0, so you can draw its transition graph. So from 0 you can only go to 1, and from 1 you can only go to 0. Then you may check that it has a unique stationary distribution given by 1/2, 1/2. Just solve the linear system as an exercise. Do it. It's very easy. So you just solve the system pi p equal pi with pi 0 plus pi 1 equal 1. So you get exactly 1/2, 1/2. But this is not ergodic, of course, because when you iterate this matrix, for n odd, you will get the same thing. For n even, you will get the identity. So p to the n does not converge in our sense. It's of ch between the identity and p itself. Okay. Third remark, a stationary distribution always exists, but it need not be unique. And I gave this, I proved this in the lecture notes. So, but I will not give it because it's a little bit lengthy and we are running out of time. So please check the lecture notes if you want to dig deeper into this. Now, we have another condition, that of regularity of the matrix P. What does it mean to say that a matrix P is regular? A square matrix, of course, a square matrix P is regular if starting from a certain rank, or there exists a positive rank, starting for which P to the n0, all the entries of P to the n0 are positive. So some power of P has positive entries, if you like. But this implies actually that starting from a certain rank, all the entries of Pn are positive. And I will prove that in this remark, actually. If this is true, so if some positive power of P has positive entries, positive I mean strictly positive, then all powers of P will also have positive entries starting from n0. Okay, not totally trivial, but it's easy. So we write just instead of saying that all entries of Pn are positive, I write Pn positive. Okay, but don't confuse that with positive symmetric, so positive definite or something. Okay. Now, why is that? So by assumption, pick n0 such that p to the power n0 is positive. And now apply the Kolmogorov-Chapman equation. So we can write pij to the n. This is just the product of two matrices. So I can write p to the n is p to the n minus n0 times p to the n0. Okay. Now, okay. Pij, so everything is non-negative here because these are probabilities. So first thing is that pij to the n is bigger or equal than 0. But I will prove that they are strictly positive. And for this, I reason by contradiction. If pij to the n is 0 for some ij, then all the sum is 0. Therefore, all the terms are 0 because they are non-negative. Okay? If the sum is 0, then all of them are 0. And now, since pkj is the kj entry of p to the n0, it's positive. Therefore, I get the other one is 0. So pik to the n minus n0 is 0 for all k. But this is a contradiction. because since this is a stochastic matrix, the sum of each row is 1. So they cannot be all 0, right? Okay, so it's equivalent to saying that so a regular matrix can be thought in 2 ways. So either a certain power is positive, or all the powers starting from a certain rank have positive entries. And now, this is the main theorem of this video. We have 3 equivalent conditions or 2 equivalence conditions for ergodicity. So first condition, xn is irreducible and aperiodic. We know what does it mean. So all periods have period 1. P is regular. We know what does this mean. And xn is ergodic. So these 3 conditions are equivalent. So this gives us an easy criterion to determine ergodicity. So either we check that this chain is one class and the period of one element is 1, of any state is 1, or one state is 1, or we compute the successive powers of P, and whenever we find a power of P with positive entries, then we know that the chain is ergodic. Okay, so we have 2 criteria for ergodicity, which is a very important condition. Okay, not all Markov chains satisfy this. Okay, only the irreducible and aperiodic, and you know that not all chains are irreducible or aperiodic. Now, 1 applies 2 actually already proved it in the previous video. If you remember, so just go back to the previous video, the last result. We showed that if xn is irreducible and aperiodic, then all the powers of P from a certain rank are positive, right? And it's important to have a finite Markov chain. Okay, so 1 implies 2 is the last result of the last video. Now, 2 implies 3 is technical, and I will not give it here. Not very, so it's just an exercise in analysis and conversions. Not very helpful, but you can read it if you like. It's written. So all the results are either proved in the lecture notes, or we give a reference where you can find the proof if you are interested. So I will not prove that 2 implies 3, but I will prove that 3 implies 1. So it's a circular proof. Okay. So assume that xn is ergodic. I want to prove that xn is irreducible. So it's one class, so all states communicate, and the period of some state is 1. So I go back to the definition. For all ij in the state space, pij to the n converges to a positive number pi j independent on I. Okay, what does it mean? If the limit is positive, okay, it means that starting from a certain rank, the sequence will be positive, right? Because it converges, right? So starting from a certain rank n0, depending on I and j, so I call it n0 of I and j, pij to the n is positive. Okay, and this proves the irreducibility. So if for every I and j there exists n such that, or could take n0 here, pi ij to the n0 is positive. What does it mean? It means that there is a path of length n0 going from I to j, but I and j are reversible. So there exists also, if I interchange I and j, so for any state j and for any state I, there is a path from I to j. So all states communicate. So this is irreducibility. Now, the aperiodicity. Okay, consider an arbitrary state I. If we take j equal I in this condition, we'll get what? We'll get a certain rank that I call m0 of I, such that pii to the n is positive for every n bigger than m or equal than m0. So there is a cycle of length n, of any length n big enough, from I to itself. And what does this mean? It means that M0 belongs to Gi, recall this set, and M0 plus 1 also belongs to this set, and so on. So we have two consecutive integers in this set, and therefore the greatest common divisor is 1. So di is 1. And that's it. Very easy. So this is our main theorem, and we shall see applications in the exercises. Please start by doing the exercises. It's very important. And you can also solve previous exams of the last 2 years. And next week, I will correct them. Okay? Now, let me end with two things. If you look at the proof in the lecture notes that 2 implies 3, you will see that convergence is geometric, so it's very fast, and you can check that on a computer. Okay, so usually after 5-6 steps, you are already there. And last result, I will not prove because it's very technical and lengthy, not instructive. It's also in the lecture notes, you can see it. If you have just an irreducible Markov chain, then actually if you set mu j to be the conditionally expected value of tj, which is the conditional mean time of first return to state j, then xn has a unique stationary distribution given by the inverse of these expectations. This is very important, actually. It's more important to apply this. So when I tell you how much time does how long does it take for in average to revisit the state again, if you have an ergodic Markov chain, then you know that the mean this average is given by 1 over the limiting distribution. Okay, and we shall illustrate this in the exercises. Okay, so actually this is I didn't assume ergodicity here, but in particular, if the chain is ergodic, then there is a simple formula for the mean times of first return, conditional mean. Okay, so that's it, and we always ask such questions about this. So we shall see in the exercises how we illustrate this. Okay, so this is concludes the video about section 1.4. Next week I will solve the exercises, but please try to do them on your own, and I will finish chapter 1. So thank you for your attention, and see you soon.